6-3, day 2. Got a few more topics on vectors as we complete our first lesson on them. Make sure you have these labeled that they are day 2. Alright, a unit vector. Basically what's going on with a unit vector is you're maintaining the same direction. Okay, remember vectors always have direction and magnitude. Okay, we're messing around with the magnitude. Alright, different vectors have different magnitudes. For example, let's take our vector v. Let's get its magnitude. Notice this vector is in component form, right? So I'm just describing it with two numbers, -2 and 5. Those two numbers are the terminal point, as I'm assuming, if it's in component form, that this vector has an initial point at 0, 0. So I just need to talk about where it ends. All right, the square root of 29, which is somewhere between 5 and 6. Okay, probably fairly close to 5.5. If I want to switch this over to a unit vector, let's call it u, same direction, but I want to switch the magnitude to 1, you take that original vector and just divide it by its magnitude. If I were to rationalize it, I would have -2 square root 29 over 29 and 5 square root 29 over 29. Okay? That's really all there is to getting a unit vector. Okay? The other thing it would allow you to do at this point, if you wanted to change this vector to a new magnitude, you're set up really well to do it. Like let's say you wanted to make a new vector that has a magnitude of 7. Well, at this, you've got a vector that has a magnitude of 1, just multiply both parts by 7, and the magnitude will be 7. One thing I am going to verify here, just to show you, this is not typically something you'll have to do, but I'm going to go back to this non-rationalized form, right, just because it's going to be a little easier for me to work with. You'll again see that that's the most common thing we do with unit vectors, is if we want to change a magnitude from one to the other, it's easiest if we scale back to the unit vector and to get a magnitude of 1, and then we can kind of, switch it to whatever we're after. All right, if I square the top, that would give me 4. Squaring the bottom would give me 29. On the other fraction, 5 squared is 25 over 29. This would simplify to the square root of 29 over 29, which indeed is 1. I was just verifying for you down here that, by dividing by this magnitude of the square root of 29, we do indeed get a magnitude of 1. Alright, so when you hear the terms standard unit vectors, here's what's going on. You could have a unit vector that goes straight horizontal, right here, okay, described as 1, 0, okay? That standard unit vector gets a fancy little name, we call it I. Okay, don't get that confused with the complex number I, has nothing to do with it, okay? Not talking complex numbers, not square roots of negatives, we're talking vectors, okay? And there's another one going vertically. If it got here at 0, 1, that standard unit vector is called J. Okay? And the next slide here, you're going to see this topic of linear combinations. All right? Where what's going on here is every vector can be written as some combination of those two standard unit vectors. Okay? think of linear combinations as just changing the notation, okay? It doesn't change the vector. It doesn't change its magnitude. It doesn't change its direction. It's just simply another way to write it. That's going to be the kind of the theme of the rest of this lesson, is looking at other ways that you can write vectors other than component form, okay? So let's talk about this vector u. Right now it's not in component form, and as is the case, let's switch it. We'll go terminal minus initial, and then terminal minus initial. Which would give us negative 3, 8. Okay? It's not a mind-blowing change here that I'm going to show you if we want to write this as a linear combination. It's a very simple switch. In example 6, we'll get to a little bit of why maybe you would want to work with a vector as a linear combination. Okay? Remember what we kind of think of like the x value, that was the unit vector of I. So we could switch this to negative 3i plus the vertical part had the unit vector of j. The I goes with the first number and the j goes with the second. Okay? Not a crazy complicated thing to do. All right? Same vector, we're just using different notation. Down in example 6, what you'll see here is that if we're doing vector operations, you certainly don't have to, right? You're going to have, at the end of this lesson, 3 different ways to write a vector. The problem and the context that you're working with those vectors might dictate which form you think is best, okay? A lot of times if you're doing vector operations, linear combinations can be easier to work with. All right, I've got these 2 vectors. There's u, and I'm introducing this new one, call it v, and this is probably the most complex operation that we've done. We're doing 2 scalar multipliers and some multiplication. All right? If you use linear combinations, all of a sudden, vector operations can really feel like working with an expression that you're pretty familiar with. I and j aren't variables, okay? But if we're using this form, we can kind of treat them like one. Whereas I'll go ahead right here and distribute the 2. I would get negative 6i plus 16j, and then distribute the negative 3 and get negative 6i plus 3j. And then at this point, it kind of becomes combining like terms. Negative 6 minus 6 would give me negative 12. 16 plus 3 would be plus 19. Okay? Linear combinations, they involve I and j. They can be a little bit easier to do vector operations with. All right, direction angles. I'm going to show you this and then give you one example. 2 examples actually working with this. So here's what's going on. Let's say, stay in the mindset here that all we're talking about is another way to describe a vector. All right, so far we've really, for the most part, used the initial form. Right, which you'll have a vector there that's going to be described in terms of x and y. Right, that vector itself is v, and typically what we've said here, and I'm not doing the linear combination thing right now. I'm going back to component form. That x value and that y value, okay, that would describe your vector. It would get you, and I'm assuming it starts at 0, 0. All right. So another way we could describe this is if we want to, number one, use the magnitude, but also every time you have a vector, it will form an angle with this side right here. That gives you another option for how to write it. Okay? Now, I need some substitutions for x and y. The cosine of this angle that is formed by that vector would be x. Okay, and really at this point, instead of just thinking about that as vector v, it's more appropriate now. Let's think about that in terms of its magnitude. All right? It would almost be like that length. Remember, when you have a vector and you're thinking magnitude, go to the distance formula. It's a lot like that. But x over the magnitude of your vector is the cosine value. And then the sine value of your angle is the y component of that vector, once again divided by its magnitude. Now, if we were to rearrange these a little bit, here's what you would get. Okay, that the angle, the x component would be the cosine value of the angle times the magnitude. And then over here, the y component would be the sine value of the angle times the magnitude. All right? Now let's go back up to here where we had v. All right? And we could write it like this. I really only need to calculate the magnitude once, but I'll just clarify what that is. And then for the two components, all I need in here is cosine of the angle and then the sine value. Okay? Instead of x and y, we use the angle and the magnitude to describe the vector. Okay? That's what's going on here. All right? So, what I'm going to focus on here, because I'm not, to get it as in the form of a direction angle, you would need to get the magnitude. Now, this doesn't say to do that, but I just want to make mention that that's probably the easier part. You would have 3 squared plus negative 4 squared. Now this one's being a little bit tricky and it's given it to you as a linear combination, so I was just thinking immediately like that. I switched it over to component form, and that's the vector we're talking about. X is 3, y is negative 4. Okay? If you were to simplify that magnitude, you would see that it's 5. All right? Now the case I'm really more concerned about is this angle. Make a little sketch. All right, so it's formed by 3 units over, 4 units down. There's the terminal point. There's my vector. Three over, 4 down. Right, those two values. There's the angle that I'm after, right? Because to go to this directional angle, once again, you need the magnitude, which we've really, that work is over to the side. I'm really focusing on the angle, and we got to get it from this, okay? More often than not, this is what comes up, right? Is I'm going to use an inverse tangent, because that's really what the vector gives me. If I think of the angle in terms of like opposite over adjacent or y over x is probably the best way to think about it. That's what I've got. Negative 53.13 degrees. Okay? I'm going to add 360 to that because that's inverse tangent in quadrant 4, right? It's going to give me that negative answer. If you did it on a calculator, that's what it's going to tell you. Okay, but then if I just add 360, which you can, I mean that you're always free to do that. I would get 306.87 approximately. Okay, looking back up to the whole directional angle thing, that would be theta. Okay, so by the way, you might have noticed over here the magnitude was 5. Those are the two numbers that I would now use to describe this vector. It has a magnitude of 5, and it is pointed in the direction of 306.87 degrees. All right, there's two applications here. The number, example 10, the second one that involves adding vectors, I'm going to hold off on that one. I just want to do this one. 10 is significantly more challenging. We'll kind of see how the rest of the unit plays out. In class, we might get to that one. All right, all I want to do here is switch forms, okay? Because basically, and this is a great example that illustrates why the different forms. Well, the problem may dictate what you are talking about with that vector, okay? Here, you'll see the direction angle form and the component form. Those numbers really represent two different things. Okay, it's the same situation, but they tell you different information. All right? Really what we have here with this plane descending at 30 degrees. Okay, let me just clarify where we're getting 210. This part of the flight travel would be like 180. And then 30 degrees below the horizontal. Right? That's where they're getting the 30. Okay? But if I'm talking of this direction angle form, I want to talk about it as 210. Okay, so any angle past 180 would mean that the plane is descending and it's going 100 miles an hour. All right, let's write this as vector v. Here, the magnitude is velocity. Okay, so I would say 100, and then for the two components, I would need the cosine of 210, and then I would need the sine value of 210. Okay, that right there is the directional angle form of a vector. Okay, I'm describing it in terms of 210 degrees. That tells me the direction that the plane is going, and then the magnitude, which is 100 miles an hour. Okay, we're going to switch it to component form, which is not really a bad switch at all. The 100 will stay out here. Essentially what I need is what's the cosine value of 210 degrees. Okay, I could go calculator and get a decimal approximation, or better yet, 210 is on the unit circle. You could go exact and see that's negative square root 3 over 2. Sine of 210, that's on the unit circle. And there we go. All that remains is to distribute the 100, which gives us negative square root 3 times 100 over 2. And then for the y, we would have negative 100 over 2. Oh, and just simplifying them here, 100 divided by 2 is 50. So for the x component, I would have negative 50 square root 3. And for the y, negative 50. Okay, so this would really now, this is in terms of velocity, because that's what this problem is all about. This would tell me this component of the vector, and then that one. Okay? This would have been like negative 50 square root 3. That number, in the context of this problem, would tell you, this problem doesn't ask for it, but I think it's interesting and worth noting, when the plane hits the ground as it lands, that's going to be the velocity that it's moving on the runway. Okay? This negative 50, that is the plane's vertical descent. Right, it tells you it's the plane, if you thought about it just directly up and down, the plane is dropping vertically about 50 miles an hour. Okay? And negative 50 square root 3, again, would be how fast it is on the runway. Both, I mean, this is the need for both of the forms, right? It's describing the same vector, but this direction form tells you, like, the velocity of the plane. Doesn't tell you how fast it's dropping vertically or the speed on the runway. The component form does. which is why we like having both forms.